Okay, so continuing our discussion about trigonometric functions, we're looking at trig functions as being either even functions or odd functions. So you can see here that the two trig functions that are considered to be even functions are the cosine and the secant. So the even function being defined by if I take the cosine of the opposite of t, then I'm still going to get the same value as cosine t, and also again for secant. Remember that odd functions, meaning if I take the function of the opposite input, then I'm going to get the opposite output. So with an odd function, the sine of opposite of t or sine of negative t is going to give me negative sine of t. And at the bottom here we could see a couple of examples where I have cosine of negative pi over 4. Well, cosine being an even function, that means that that's going to be the same value as cosine of pi over 4, which we should be working on memorizing as being square root of 2 divided by 2. Okay. Likewise, I have tangent of negative pi over 4. Tangent is an odd function, so that means it's going to be the opposite of tangent pi over 4. And since the tangent of pi over 4 is 1, the opposite gives me negative 1 as a solution. Okay, so just again extending that idea of even and odd functions that we did first semester and applying that to the trigonometric functions. Okay. We've got a few what are called fundamental identities, and these pretty much make sense if you think about them. Since we know that sine of t is equal to y and that cosecant of t is 1 divided by y, if we were to take this sine of t and substitute that in place of y, that would give us cosecant t equaling 1 divided by sine of t by simply doing some substitution. Okay? And this type of substitution can be done for all of the trig functions and leads to what we call the reciprocal identities. Okay. So here are all of our reciprocal identities, which can be found by doing just what we did in the previous slide. The sine of t is the reciprocal of the cosecant. If I take 1 over cosecant, then I get sine. And likewise, the cosecant being the reciprocal of the sine, if I take 1 divided by sine of t, I'll actually get cosecant of t. You can see that the cosine and the secant are reciprocal functions. Okay, secant, cosine, and then tangent and cotangent are also reciprocal functions. Okay? So these are what we call the reciprocal identities, and we've kind of hit around and hinted around at this when we were doing our trig functions using the x's and the y's. Next are what we call the quotient identities. Okay. And again, kind of going through this process, we know that the tangent of t is defined to be the y-coordinate divided by the x-coordinate. And since we know that sine of t is equal to y and cosine of t is equal to x, again, we can do some substitution, and that would lead us to the tangent of t really being the sine of t divided by the cosine. And since tangent and cotangent are reciprocals, that means that the cotangent is the cosine divided by the sine. Okay? So again, these are a couple of what we call the quotient identities because we have a quotient on the right-hand side of each of those. Okay, so if we look at an example applying those quotient identities, if we're given that the sine of t is 2/5 and that cosine of t is the square root of 21/5, then we can find the remaining trig functions using all of these relationships, whether it's the reciprocal or the quotient. Okay, so the tangent of t, remember we just defined tangent as being the same thing as the sine divided by the cosine. So I know that the sine of t was 2/5. I know that the cosine was square root of 21/5. That would simplify because the 5's would divide out here, leaving 2 divided by square root of 21, which when we rationalize that denominator gives us 2 square root of 21 divided by 21. Okay. The cotangent, I have cosine written there, that should be cotangent of t, is the reciprocal of tangent, so that's cosine divided by sine. So we plug in square root of 21 divided by 5 for cosine, 2/5 for sine. Again, the 5s would divide out when we multiply by the reciprocal, and we'd end up with the square root of 21 divided by 2 for our cotangent of t. Secant is 1 divided by cosine. So I insert the square root of 21/5 for cosine of t, giving me 5 divided by square root of 21, because this here means take the reciprocal. 1 over means reciprocal. So when I flip it, I get 5 over square root of 21, and when I rationalize, we end up with 5 square root of 21 divided by 21. And cosecant, the last one, cosecant being the reciprocal of the sine. Well, we know the sine is 2/5, so 1 divided by 2/5 gives us simply 5/2. So we can use these reciprocal and quotient identities to fill in the rest of the trig values given one or two of them to begin with. All right, and so if we recall the unit circle, remember the unit circle was defined as the equation of x squared plus y squared equals 1. And since we know that x is really associated with cosine of t and that y is really the sine of t, we can substitute again and get a new equation here with cosine t squared plus sine t squared equals 1. And we can rewrite that. Instead of the parentheses around the whole sine t, we can take this squared and we can slide it in here right on the sine. So giving me sine squared of t and cosine squared of t. Remember, the addition doesn't matter what order we go in. That's the commutative property. So sine squared of t plus cosine squared of t equals 1, and that is what we call a Pythagorean identity, because it's actually all kind of derived from the beginnings using Pythagorean theorem. So that is one of the Pythagorean identities. Okay. So we actually have 3 Pythagorean identities we're going to be using. The sine squared plus cosine squared is 1. We'd have 1 plus tangent squared of t is equal to secant squared. And we'd have 1 plus cotangent squared is equal to cosecant squared. And they can all be derived in basically the same way that we came up with that first equation, by making some substitutions and doing some simplification. Okay? But these are the 3 trig Pythagorean identities that we're going to need to know. Okay? So if I know that the sine of t is 3/5 and t is between 0 and pi over 2, then I can use that sine value to figure out the cosine by using the Pythagorean identity. I know the sine is 3/5, so sine squared of t means 3/5 squared, plus cosine equals squared equals 1. So 3/5 squared is 9/25. When I subtract that from both sides, I get cosine squared equals 16/25. So by taking the square root of both sides, normally we would have a plus or a minus, but when we look back up here, if t is between 0 and pi over 2, okay, I know that the cosine of t has to be positive, okay, because we are in the first quadrant and cosine is x, and cosine would be positive in the first quadrant. So therefore, the cosine of t is simply 4/5. Okay. When we talk about trigonometric functions, they're examples of what we call a periodic function. Okay. A periodic function, we've kind of mentioned it, how it just kind of keeps repeating itself. It happens the same pattern over and over and over. So when we're looking at a periodic function, we're saying that if we take f of t plus p, some value, we're still going to end up with the same value as f of t. So p is going to be some positive number. And the smallest value of p for which f is periodic is called the period. So whatever that smallest value is that I add that always gets me back to the same value is what we call the period. So if we look at sine and cosine, if I take the sine of 2 plus t, or t plus 2 pi, the sine of t plus 2 pi gives me the same thing as the sine of p. Remember when we were talking about coterminal angles? We added that 2 pi and we said it brought us back to the exact same location. It just made a one complete revolution to get back to it. And the same thing with cosine. If I have the cosine of t plus 2 pi, that's going to be the same value as the cosine of t. And what that tells us then is that the period of both of those functions, the period of the sine and cosine functions, is going to be 2 pi. So every time I go 2 pi radians, I'm going to end up back at the same value every time. When we look at the tangent and the cotangent, the period for tangent and cotangent is simply pi. We're only going to make a half a revolution to get back to the same values. Okay? And if you think about when we were talking about the unit circle, we knew that the tangent was positive in the first quadrant and it was positive in the third. Okay? So if we think about a straight line through there, that rotation there would be a pi radians rotation. We knew that it was negative in the second, and it was also negative in the fourth. So again, that's only going to be a rotation of pi rather than a full revolution like we saw with the sine and the cosine. So as an example here, if I want to find the sine of 9 pi over 4, 9/4 pi, well, I can rewrite 9/4 as 1/4 pi plus 2 pi. And because that is the idea behind these being a periodic function, with the period being 2 pi, the sine of t plus 2 pi, remember, was equal to the sine of t, so this would give me the same value as the sine of pi over 4. Because this is going to be right back in the first quadrant. This angle is going to be in the same location as pi over 4. And the sine of pi over 4 is square root of 2 divided by 2. So I know that the sine of 9/4 pi is equal to square root of 2 divided by 2. Because of that idea of being a periodic function, that the values are going to keep repeating themselves every 2 pi. Tangent. If I have the tangent of negative 5/4 pi, well, I use the idea of even and odd. Tangent is an odd function, so that's the same thing as the opposite of tangent of 5 pi over 4. 5/4 is the same thing as pi over 4 plus pi, and there's that idea of period again. So pi over 4 plus pi is going to be the same value as tangent of pi over 4. Well, the tangent of pi over 4 is 1, but since I have a negative out here, I know that the tangent of negative 5 pi over 4 is actually going to be now negative 1. So we will do some more work with these tomorrow in class, so we will see you then.